Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Oh, perfect. Okay. First of all, okay, thank you very much for the invite. I'm really happy to be here. And apologies for changing the talk, because I announced a talk on bounded rationality. But if you've never been exposed to it, then it was going to be too specific. So I decided to change it with something that tries to encompass a little bit all the work that I have done. And I realized that I could organize the material around 3 key concepts that I'm going to talk about today. So first of all, I just want to explain a little bit what my motivations are. So I'm interested in the mathematical foundations of intelligent behavior. So perhaps the term is a bit old school, but I'm interested in cybernetics. And in particular, I'm interested in the intersection between 3 areas, a little bit of psychology, and mainly machine learning. And something died here. Whoops. I have no idea. Yeah? I'll disconnect and connect again to see whether. I think my laptop just.
It's the laptop that died with it.
Of course, this never happens. It happens right when I'm giving a talk. Okay, let's see. Maybe I should switch to Microsoft Office. Okay. That was strange. I apologize for that again. Okay, as I was saying, I'm interested in this intersection. And the 2 main areas are machine learning and theoretical economics. So basically, I'm interested in machine learning, but I have this additional constraint that if I'm going to design an algorithm, it has to be somehow justified also from principles that are taken from theoretical economics. So, and this is the outline of my talk. First, I'm going to talk about expected utility theory, which is the foundation of agency that we use in, for example, in reinforcement learning. Then I'm going to talk about the role of causality in agency. These are the 3 key ideas. So causality in agency, then adaptation. How do we come up with a behavior that is universal over a given class of behaviors? Then the final one will be bounded rationality, and then I will conclude. And the setup I have in mind is the following. So I have 2 systems that interact with each other. The first one is the world, which is given and is typically unknown and has to be discovered. And the second one is the agent, which is the one designed by the engineer. And the 2 of them take turns, interact, and exchange symbols. So the agent produces actions, the world replies with observations, and they're drawn from distributions that are conditioned on the past interactions. And as we observe these interactions, they define, the interactions define an interaction sequence. For example, this one here, which is like, you can think of it as numbers being written on a tape, where these numbers correspond to the ID of a particular action, which can be drawn from a countable set, or if you want to generalize this, you can also think of an uncountable set. Now, the world can be any stochastic process. So in particular, it could be a multi-arm bandit, a Markov decision process, a POMDP, or, as I said, any other controllable stochastic process. So it's important to remind ourselves of where expect utility came from. It's actually, expect utility theory is so entrenched and is so natural to us nowadays that it's very hard to imagine that there was a point where it wasn't so obvious. Okay. So it started basically with Bernoulli, who tried to solve the St. Petersburg paradox, and he realized that people don't optimize return, but they optimize some other function that is personal to them, okay, which he called utility. I won't go into the details of how this was derived, but this is basically the birth date of the concept of utility. And then in 1921 came up with the following key idea, that actually decision makers take account the uncertainty in order to make rational decisions. So someone had to postulate this. Then a major advancement came from Ramsey and Definetti, who operationalized the notion of subjective probability. So before that, it was some sort of a vague concept, but they defined it operation in terms of a betting attitude. Something similar was done later by von Neumann and Morgenstern. They came up with the idea of expected utility, where you take a decision maker, you present a decision maker with choices, and then you tabulate all the answers, the preferences, and from these preferences you can then infer a unique utility function. So importantly here, utility, because nowadays we have somehow reified the concept of utility. We start from the concept of utility, we take it as a given, but originally it was defined as something that you can regress on. Okay, so something that you derive from behavior. So Savage then later came up with the idea of combining expect utility theory with subjective probability, and he came up with a different scheme in which decision makers, if you tabulate their choices, you can infer two mathematical objects. The first one, a unique probability measure over the outcomes of the world, and the unique, up to a finite transformation, unique utility function in one framework. And this is basically the bedrock of modern economics. Okay, so when you do, for example, in reinforcement learning, you solve for the value function and things like that, it all comes from this. These are all theorems of this foundation here. Okay, not much time passed until someone realized that actually expected utility theory doesn't really scale. It works well when you have microworlds, when you have, for example, 10 different choices. But if you have, like in reinforcement learning, where you have you want to plan over a horizon of perhaps 100 time steps, you have an explosion of possible policies there. And then this theory doesn't work anymore. And so this was basically the main motivation of my work and my PhD studies. Is there an alternative to this theory that makes sense from a computational point of view? So there is no widely agreed upon theory of bounded rationality today, but I'm going to talk about three ideas of how to tackle this problem. So as I was saying, a consequence of subjective expected utility theory is that when you consider an agent that interacts with an environment in steps, and you don't know the environment, then you place a distribution over all the possible environments. This gives you a mixture distribution, and this mixture distribution has sufficient statistics that are unbounded. And so in the end, you end up solving a decision tree, like this one here, that grows exponentially in the planning horizon. And to solve this problem, you have to solve recursively the Bellman optimality equations, which then defines which are the optimal actions here in each one of these decision nodes, marked in red. Now we see immediately that this, in theory, it's actually very easy because you just choose the policy that maximizes the subjective expected utility, and it bypasses all the problems that you usually encounter in reinforcement learning. It solves automatically the exploration-exploitation problem because it's by definition, by construction, it's optimal. But obviously, this is intractable. And it's intractable due to two reasons. The first one is kind of obvious. It's because the number of sufficient statistics is just too large. So the policy space starts growing exponentially with the planning horizon. But the second one is a bit more subtle. It's essentially because the policy choice has to causally precede the interactions. So you have to find the optimal policy first. You have to unroll all the possible lives of the agent, calculate the optimal policy, and then you start interacting with the environment. It's like it sounds like a waste of computational resources. How come you come up with the optimal action for an environment that you have never seen? So 3 ideas. The first one is going to be that actions are causal interventions. The second one is that if you want to achieve universal behavior, how do you build the universal behavior? That's easy. You do an M projection, and you get the Bayesian mixture. So that's the second point, that Bayesian mixtures are universal over a given class of environments. And the last one is that utility can be thought of as an information constraint. So let's review first causality. And for this, let me try to motivate this from a simple example. We have a graphical model. We have a graphical model over a stochastic process. It's just a simple sequence, x1, x2, x3, x4, and so forth. We don't know the parameter. So we place a prior over the hypothesis space. And this is the likelihood function. And now we make observations. Let's say we observe the first 2 values. So we condition our model on these values. And we can calculate the posterior over the hypothesis by just multiplying the prior with the likelihood. Now, let's assume that someone asks us to generate some examples now. So I come and I generate x3. Okay, so this is my simulated example that a value that I draw from the posterior predictive distribution. And now the question is, OK, I start generating this data, and then suddenly I tell myself, hey, wait a minute, can I take this data that I have just generated and condition my model on this data? Now, obviously, this doesn't work. I mean, this is like a machine learning heresy, OK? But so in some cases, this would be something desirable. Let me explain why. So if I wanted to insist on conditioning on data that I have just generated from the very model, how would I do that? Well, if we insist, then the first observation is that if you generate data from your model, and now let's say you want to take it and condition your model further on it, it should not change your beliefs. Because this data is a reflection of the current state of knowledge. So you have the prior, and this would be your posterior, where you have the prior again multiplied by the likelihood. This likelihood is a modified likelihood, because obviously it cannot be the original likelihood. We have to do something to our model for this to work. Some modification. So what would be this modification? Well, if the posterior and the prior are proportional to each other, then necessarily the likelihood model has to be independent of the parameter. And once you condition your model on the parameter, it doesn't really matter how this distribution originally looked like, as long as the simulated data is in the support of this distribution. So in particular, I can choose just the delta function here. Now, this operation that I just did, taking this piece of the graphical model and this piece here of the graphical model and replacing it with this Q, and in particular this delta function, that's a causal intervention. Okay? So the causal intervention is, in a sense, telling the model that the data doesn't carry evidence. So how does this look like? Well, it's very simple. I generate x3. I do the causal intervention. It removes this incoming arc here. But it has still effects downstream in the model. As long as this graphical model has causal semantics. So out of all the possible factorizations of your joint distribution, it represents, this one is the one that represents the causal order, or the functional dependencies between your random variables. So how does this look like from a measure-theoretic point of view? So here we have the random variable x1, x2, and x3. And we do conditioning. So we condition on the second random variable on the observation 1, which means that I now I search for all the realizations of the stochastic process that are incompatible with this observation. I remove them, and I renormalize. That's just conditioning. In the causal case, what I do is I remove the incompatible realizations, but downstream of the causal intervention. And I renormalize only these pieces. That's the difference. OK, so as a summary, the problem is that simulated data should not create evidence when we condition on it. The key idea here is to use a causal intervention, because the causal intervention erases the evidence by removing the dependency to the functional preconditions. And the properties are, well, it's something that operates directly on the probability measure. And the actions of an agent, if you now, typically when you design a reinforcement learning agent, you think of the prediction model as being, let's say, a graphical model, and the policy as being something separate that uses the graphical model. Now, try to internalize the policy into the graphical model too. If you do that, then you get that actions are random variables, and that the actions have to be treated as causal interventions. And this can also be extended to measure spaces, but then you need to put a partial order over the. First of all, measure theory is not enough. You need to impose some causal structure over the sigma algebra, and a generator of the sigma algebra. OK. Second part, universality. So how do we learn an optimal behavior? Well, let's consider the following problem to motivate it. So we have a sequence prediction problem. We have 3 sequences here. So the first one is 1, 3, 5, 7, 9, 11. Which one would be the next? That's kind of easy. It seems to be just the odd numbers, no? 13. And that's the rule. The second sequence is 1, 4, 9, 16, 25, 36. 49. Great. The last one, 1, 2, 3, 4, 29. Because it's drawn from this polynomial here. No? So what I want to illustrate with this is that the induction problem, well, this is the induction problem. We want to infer laws from examples. But there is no unique solution to the induction problem. So what would be the principle we want to use here? So this is important in agency because because when you have an agent, the agent has to be able to predict the responses of the environment, and it has to understand the effects of its actions. So let's go back to this example. Now we have the agent that is interacting with an environment. It has experienced 2 observations so far. These observations, since the agent has a probabilistic model over these observations, it can use them to create a code. So this is a binary encoding of these 2 observations. And this binary encoding can be thought of as a proxy for the modifications that have to be carried out in the data structure that represents the beliefs of the agent. So whenever it makes an observation, this triggers some changes in the belief structure, which can be, the cost at least, can be represented as the length of the binary sequence or binary encoded command that you need to execute in order to reflect the conditioning on this last observation. And we know from information theory that prediction and compression are essentially the same thing. There's 2 sides of the same coin. And these experiences imply minimal changes to the belief structure of the agent. So the question now is, can we minimize these changes? And the answer is we can. So the way this works is, if you want to construct an optimal adaptive compressor, if you just want to create a compressor, it's kind of easy. You are given a description of the stochastic process. You use the probabilities to construct an optimal code. But what happens in the case when you don't know the identity of the source? So you take all the possible sources. In this case, there's only 3. And you now consider the convex set spanned by these guys. So each one of these stochastic processes is now a vertex of your convex set. And now you minimize the cross entropy. You construct a new stochastic process that is the minimizer of the cross entropy to the average source. Now, the cross entropy has an incompressible part, which is just the entropy, and it has another part, which is the DKL, the Kullback-Leibler divergence. And so that's really the part that you want to optimize. So when you do this, you get the M projection. Okay. So this guy here is going to be the one that minimizes the distance to the average stochastic process. And it's actually very simple because it's just going to be an average of the original stochastic processes. That's your Bayesian mixture. And it has the property that if you condition on data generated by one of these guys in the vertices, then the posterior predictive will converge to the true distribution. So we know this, so I'll skip it. So OK, that's for the prediction part. But what happens now in the action part? So let's continue with this story. We have the agent again that has made two observations, has issued an action, made an observation. This is the encoding that reflects how the agent had to change its beliefs to record this experience. It generates an action. This is the encoding of the command to change the beliefs. And now the question is, can we minimize this encoding here? Can we apply the same idea that we use for prediction to the action part too? And actually, we can do that. And that's when you get this rule here. So the idea, again, is that you have a set of stochastic processes that represent optimal behaviors between an agent and an environment. And you just take the mixture of them. And now you get experience. You condition on this experience. And you look at the posterior predictive over your actions, which suggests the next action to take. So you just sample from it. But there's a caveat here, that the past actions, when you condition on them, remember that these past actions now, these actions are drawn from the model itself. Therefore, if you want to condition your graphical model, say, on this action that you have just generated, you need to treat it as a causal intervention, precisely for the reasons we saw in the previous section. If you do that, so you end up sampling your actions from the posterior predictive, where, as I said, the past actions have been treated as causal interventions. This guy here, you can expand it to make the mixture explicit. And it can be implemented algorithmically by just first sampling from the posterior and using the sample parameter as a plug-in parameter to generate the action. That's Thompson sampling. OK? So let's see an example. Very simple. So we have a scenario where we have two doors. Behind one of these doors, there's a prize. Behind the other one, there's a goat. There's two possible worlds. The prize is behind door 1 or door 2. In world 1, your action would be to open door 1 because you know that the prize is there. In world 2, you open door 2. OK, so you have two random variables, one for your action, one for the observation. Now, we assume that we don't know in which world we are, so we take the mixture. This gives you this mixture model here. How do we use it? Well, if we assume that the prior over the optimal actions is just, over the two worlds is just 1/2, then we can just query this model for an action. And it's going to tell us that we can just flip a coin, a fair coin, and then choose that particular action. So let's do that. Let's say that we flip a coin, and it tells us to open door 1. So we go, and we open door 1. But as we open door 1, if we don't treat our action as a causal intervention, then we basically trick ourselves into believing that the price is therefore behind door 1. And the causal intervention is precisely avoiding this. So the intervention essentially is a mechanism that tricks the agent into believing that it intended to take that action all along. Okay, so applications, this can be applied to multi-arm bandits. I'm pretty sure you're very familiar with this. Okay, so multi-arm bandits, model-free reinforcement learning, LQR. This is just a list of the things that I have done in the past. But obviously, if you look into the literature now, there is a lot. I mean, it's just if you look at the dates, back then, this was not so obvious. So as a summary, the problem is how to model behavioral universality. The key idea here is to use a Bayesian mixture over behaviors and treat past actions as causal interventions. And the properties are that in the end, you get a stochastic controller that adapts with experience. So it doesn't choose the policy right at the start, but it infers the policy as the data arrives. It exploits a built-in reward mechanism in Bayes' rule. Because if you think of Bayes' rule as being a prediction strategy, and you want to understand what is the cost function that is being optimized by it, you get back to this M projection. And so when you do, for example, reinforcement learning, and on one hand you have a Bayesian model to predict the environment, on the other hand you have a utility function, it's kind of weird because you're using two different utility functions to solve a problem. The policy part with some arbitrary utility function, and the prediction part with the M projection. So why don't we just use the same for everything? That's exactly what we did here. So we are just optimizing compression, and the maximization of utility is an afterthought that is embedded into this, into Bayes' rule now. Okay, and this is the last part. So let's remember again, expected utility. All you have to do is just maximize the expected utility. That's your optimal action. Okay, so you have two urns here. They contain red and white balls. And you have to pick one of these urns. I'm going to then randomly withdraw a ball, show you the color, and if it's red, you win. Which one would you pick here? Oh, obviously the left one, no? Easy. Now? Right? Okay, so actually this is the so-called Ellsberg Paradox. It seems kind of trivial, but this was the first big blow to expected utility theory. Most of the people choose this one here. But if you think about it, if you put on the economist hat, then you would say, well, I don't know what the proportions are here, so let me list all of them. It gives you 101 different combinations. So let me place a uniform prior over them. And let's marginalize over it, and as a result, I get 50-50. So the two of them are actually identical. Okay? Nevertheless, most of the people choose this. And then you can come and say, well, they're just not rational. But there is a caveat here. Ellsberg, at the time Savage was still alive, and Ellsberg asked Savage, the creator of subjective expected utility. And his answer was, well, obviously, I will go for this one here, because this is not a risk situation. It's not known probabilities. There are unknown probabilities, and they affect your behavior in a different way. These are the so-called ambiguities. These are probabilities that you have not rationalized. Your action is not a function of these probabilities. So in a sense, you can say that the unknown probabilities have an impact on the net value, on the net worth of a particular outcome. Second example, pick the largest here. Yes?
You made an implicit assumption in your utility that there's a uniform distribution over the number of red balls in the right-hand urn. But in fact, that prior could be any number of an infinite space of models, and there's not really the reason why.
Of course, that's true.
That doing it rather than as an unknown, it's just you can't marginalize over it effectively. So.
Sorry, I didn't understand the last part.
The space is too big to marginalize over.
Yes, that could be one explanation. But it's here. The main point is that these probabilities are unspecified. So it's different. So in economics, there is a distinction between risk and ambiguities. Both of them are probabilities, but risk are the ones that you use in your deliberation to come up with an optimal action. Ambiguities are probabilities that are the unknown unknowns.
Can we affect people's prior by presenting them with different
so in experiments, basically, when you expose people to this earn task repeatedly, they end up converging to the maximum expected utility principle. So it's as if they've somehow internalized assuming that, let's assume that behind this there is basically the same earn, that the two of them are identical. Okay. Actually, I didn't explain why this is a paradox. So basically, people choose this earn here. And then they ask, well, okay, before I draw a ball here, I'll change the rules of the game. You win for white. Choose again. So people would switch. If they were consistent with expected utility theory, they would switch now, because them choosing the left earn is basically reflecting the fact that they think that it's somehow adversarial, and here there are just less red balls. And therefore, they should switch when they ask them, that they tell them that they actually win for white. They still stick to this one. That's what you observe experimentally. Okay. Pick the largest straw here. Easy. Top one. Try again. So when you are planning, when you are building an optimal controller over an unknown environment, it doesn't look like this. It looks like that. Picking out the optimal policy is like finding a needle in a haystack. It's practically impossible. So it just doesn't make any sense. We need to find a way to redefine the problem or find a different optimization rule here. Otherwise, we're always going to design algorithms that are approximations. So I want to find the optimal controller, but my algorithm actually approximates it, and then the other algorithm approximates the other thing. You don't want approximations. You want a theory that reflects what you're doing. So, and on top of that, in this particular setup, you can't do better than random search, because it's completely unstructured. There is no symmetry that you can exploit to define equivalence classes and then say, okay, let me explore this guy, let me test this representative of this class, and then move to the other class. It's impossible. You cannot do better than just random search. So, okay, this brings me to the last part. Here, actually, there is a mistake here. Okay. There is a mistake here. These guys here, the vertices here, are three possible actions, not distributions. Okay, these are just three actions, so delta functions. And this is a prior. This is your prior behavior, your prior choice, before you have done your deliberation. Then the utilities arrive, and the utilities are essentially imposing a linear constraint on this set. What you do now is you compute the E projection. The E projection, remember before we had this guy here at the bottom, and now we have it at the top. And the E projection is the one that minimizes the DKL subject to this constraint. So the difference to the other one, because sometimes people ask, the difference to the other DKL is that the other DKL is like an OR operation. And this guy here is an AND operation. It incorporates a new constraint. This is all from information geometry. So this is the decision-making framework I've been working on for the past few years. So a decision maker can be thought of as transforming a prior behavior, prior choice probabilities into posterior choice probabilities. And it can be characterized as maximizing the free energy functional. The free energy functional is just the expected utility regularized by this DKL, which is, if you look at it closely, this is the E projection. So we have different components here. As I said, this is expected utility. This guy here is just the Lagrange multiplier, if you want, or it's just the inverse temperature, which controls the quality of your answer. And this models large-scale choice spaces, trust and risk sensitivity, and other information constraints. So if we solve this, the optimal solution to this optimization program has a closed-form solution, which is given by this guy here. So we define the solution as being the posterior choice, which is just going to be the prior times the likelihood. And the likelihood has this structure here. As I said, inverse temperature and utility. If we take the optimal solution and we plug it back into the free energy functional, we get the certainty equivalent. The certainty equivalent is probably the most important economic term. When you have an uncertain choice, a distribution over possible outcomes, each one of these outcomes has a different utility. How do you summarize this value? In expected utility theory, you summarize it by taking the expectation over the utilities. Therefore, the certainty equivalent is the expectation. But in this case, we have a wide range of different operators depending on the choice of alpha. In fact, if we take the certainty equivalent and we vary alpha, we get this sigmoid here. When alpha is equal to 0, we recover the expectation. When alpha is positive, it starts approximating the max operator. When alpha is negative, it starts approaching the min operator. This is important because remember when you, for example, when you have adversarial environments or you play Go or something like that, then you have to use different decision rules depending on the kind of agent you're interacting with. So for example, you use Expectimax when you're dealing with a stochastic environment. You use Minimax when you're dealing with an adversary, etc. Under this view, all of these basically boil down to the same decision principle with different inverse temperatures. So for alpha 1, the distribution over choices looks more or less like this, where the decision maker becomes somehow anti-rational and tends to choose, these are ordered according to utility. So the decision maker tends to choose bad choices. This is just the expectation, so it falls back to the prior. And this is approximating a max operation. So it puts more probability mass on the better outcomes. So, and the interesting thing is when you solve this, the solution has an operational interpretation. So the way you can choose is by just obtaining samples from the prior and then doing rejection sampling. You have some desired target utility, and you end up comparing it with the utility you get from the random sample. And using rejection sampling, stochastically, you will decide whether you keep the sample or not. So you can achieve things like this. So here on this axis, we have the utility, and here we have the inverse temperature. As you increase the inverse temperature, you see that the performance in utility starts increasing. At the same time, this is the number of inspected choices. Okay, so the number of rejected samples in rejection sampling, say. As you increase the inverse temperature, this thing starts increasing too. But the important point the important thing to notice here, this looks almost linear, okay? But the important part to notice here is that this is actually concave. So if you want to improve upon this value here, you need to do a lot of search effort. So the marginal gain in utility is decreasing in the search effort. So there is no real optimal solution here. It's just a trade-off. You have to decide which trade-off you want between search complexity and the quality of your answer. Now let's get back to the certainty equivalent value. These are the classical operators that you would find in game trees. So this is the min operator. This is just a chance node. And this is the max operator, which is usually the decision node, the node reflecting the actions of the agent. These can be approximated now. So if you take a bounded rational choice, by setting an appropriate inverse temperature, you can approximate these operators here. Which means that now you can approximate any game tree with the bounded rational tree where you approximate each node by setting the inverse temperature. And remember that we can solve this tree now by sampling, by forward sampling. So you don't have to apply dynamic programming, but you start sampling, generating rollouts from this tree until your rejection sampling algorithm accepts a sample. And if we now focus on two-step decision trees, and let's assume that this node here corresponds to the agent's action, and this corresponds to the environmental action, and this guy here has an inverse temperature alpha, and the other guy, the environment, has an inverse temperature beta. It's interesting to see that by choosing alpha and beta, you obtain the decision rules that you would get in classical economics. So am I running out of time? Yeah. So you have, for example, this is the Minimax. This is Expectimax. And here you have some bounded rational versions of it. So for example, here on this axis, if you change alpha, you can move from anti-rational to rational. Or if you move beta, you can move from risk-averse to risk-seeking behavior. So there is a whole continuum of possible of risk attitudes. And in particular, the Ellsberg Paradox here, if we want to model it, we have a first step where the configuration of this urn here is drawn. There is 101 different configurations. We place a uniform prior over them. But the inverse temperature of this particular node is negative. So it means that you think this choice is going to be adversarial. So the posterior distribution is going to be drawing, is not going to follow this with the uniform law, but is going to tend to pick the worst outcomes. Applications, these are not mine. So you're probably familiar with Bert Kappan's work, path integral control, or Todorow's linearly solvable control. I mean, these are related. Tishby and Polanyi have worked on MDPs with information constraints. A friend of mine, Evangelos Theodorou, has worked on real-time control of quadcopters. Then in Daniel Brown's group, a colleague of mine, he has worked on spiking neural networks and on emergent abstractions using this framework. So as a summary, the problem here was to tackle large-scale decision spaces. And the key ideas here were first to regularize the choices, and second to exploit this stochastic computational model. And the properties are that it blurs the boundary between learning and planning. And it's massively parallelizable, because I didn't speak about that, but you could see that if you want to generate a sample, you can, in principle, do this in parallel. It's of controllable complexity. By changing the inverse temperatures, you can basically choose the size of your solution space. And it's also sensitive to higher order moments of utility, because if you regularize with the DKL, basically you're just saying that you don't care only about the expected utility, but also the variance and so forth. And it implements a rich class of decision rules. So that will be the end. So as a summary, the problem is that expected utility is not suitable for AI. It's useful as a gold standard. But if we want to characterize what our algorithms are doing, it's not suitable anymore. I'm not claiming that I have a solution for it, but it's an approximation from a probabilistic point of view. The key ideas here are the following. So first of all, we treat actions and policies as random variables in your model. And therefore, you have to use causal interventions to distinguish the internally generated values from the externally generated values, the ones that carry evidence. To achieve universality in behavior, what you do is you just give yourself a class of possible behaviors and you mix them. So, and finally, you treat utility as an information constraint. So these are collaborators. This is the most important slide of the talk. So these are former collaborator Daniel Brown, his group, Kyung Kim from KAIST, Daniel Lee, UPenn, Tyler Tishby from the Hebrew University, and my supervisor, Zubin. Thank you very much. Yep.
I have a question on the example slide where you showed the mixture between three stochastic processes, right?
Yes.
So, and using universality within a restricted class like this finite mixture, I can understand you can recover any mixture component with enough samples. But it seems to me that in general it would be quite difficult to place a prior process over a large class of stochastic processes, right? So kind of to really achieve universality as in Hatter's work. In fact,
you mean, for example, in the uncountable case?
Yeah, uncountable, or depending on your observation space and action space, the class of stochastic processes is so large that even placing a prior process on that class is potentially quite difficult, right? I mean, there's this result of Hatter's AIXI, the negative results on that basically it says it's almost impossible, right? For universal computational processes, it's impossible, right?
Yes, you're talking specifically about the Solomonoff prior, where you take the mixture over all the computable environments, essentially. Then, yeah, you get a non-computable semi-measure. It's true. Yeah.
So you have to somehow carve out an interesting subset. So how
Yes.
do you do that? Is it, or do you mean a different thing with universality? Maybe I'm confused. What do you mean with universality?
No, universality in the sense that if you give yourself a class of stochastic processes that you're interested in, and then you construct a universal predictor of them. So the Solomonoff predictor is universal. That's true. This is, theoretically that's a fact. Now it's non-computable. That's also true. So deciding how to choose, how to carve out the class such that the mixtures then result in a computable measure, I don't know a general result that tells this distinction.
Another question, this is maybe a really simple one.
Yeah.
So you freely combine just utility functions with, as a kind of, almost like a Gibbs energy term, exponential minus utility,
Yes.
right?
Yes.
So is it always possible? I mean, the utilities could be on a vastly different scale, and you only have this one parameter which can sort of shrink this entire scale.
Yes.
So is this just a minor technicality, and you can always, any utility function which is non-negative or something can be accommodated, or is there some further restrictions on the type of utilities that you can handle?
That's a good question. I would say, in principle, I cannot answer this question. Because I think there is no restriction. Okay, but I have not seen a theorem that would deny this. I'm not aware of a theorem that tells me that actually that these shapes are arbitrary. Yeah. Yeah, I don't know the precise answer to your question. For all practical purposes, you can do whatever you want. Yeah.
Weird.
So when you want to link learning with compression, one way I can imagine is resonance, MDL framework, or normalized maximum likelihood.
Yeah.
But there is a big problem. It gets really messy if you want to go from discrete stuffs to continuous stuffs there. So do you have any idea how you can do more general class of learning algorithm and make the link between, or that is not the kind of thing you're thinking about, or their approach is basically minimax, right? Is that the kind of link you want to build between learning and compression, or do you have any other idea?
No. In my case, So I wouldn't know how to. There is one part of measure theory that I don't know how to connect with information theory, which is precisely conditioning on events of measure theory 0, which is essentially what you're asking. So there is no clear connection there. So, and I wouldn't know how to answer this. So all the events that I'm considering are events that have a non-zero measure. So it would always be over a measurable, let's say Borel set.
Another more general question. So in the last part of the talk, you say basically when the agent changes the beliefs, that amounts to work, right? So that's the kind of work for the agent, and then sort of the trade-offs off for bounded rationality to make a good choice and minimize the work that's spent, right? Yeah. But in a way, maybe the agents are very different. So maybe an insect brain is very different from my brain. Is maybe very different from a piece of silicon that we developed, right? So should there not be also a model of the amount of work required to do this belief change?
That's an active area of research, yeah. So I think what you're trying to point at is like an objective function that characterizes intelligence, perhaps. Like, for example, the legs universal measure. This somehow...
Right? So maybe it's simpler to just say how much energy it would take to change beliefs or something like that.
Exactly. So this is being investigated now. So perhaps another measure would be to minimize the mutual information between your predictor and your policy, subject to constraints. And then you don't get a universal measure, but you get a family of measures, depending on what their constraints are. But as I said, this is being investigated now.
You already touched on some areas of related work, or future work, sorry. Could you just briefly outline kind of what the key questions are that you would want to follow up on, or that you would want to work on in the future?
Well, actually, I'm a bit interested in seeing applications of this. Yeah. So I'm interested in seeing how this applies to, for example, probabilistic programs. And the question that you touched upon right now. Okay, the measure, and a measure of performance, or the family of measures of performance. Yeah, that's it.
So there are many different frameworks for bounded rationality, right?
Yes.
So some are more descriptive on how humans act, right?
Yes.
Which is interesting, and some are more, prescriptive how we should build systems.
Yes.
So the one other framework I know of is computational rationality. Can you just make a brief comparison to that work?
Okay. So there is this other framework called computational rationality, which relies mainly on something called meta-reasoning. The idea here is that an agent, when the agent has to choose an action, he is also considering the cost of finding this action. These costs are the computational costs. Okay. This is different. The reason why this is different is as follows. In this particular case, when the agent is capable of doing meta-reasoning, then by the action of stepping into the meta level, you are incurring in the costs of thinking about the costs of your choice. So to solve this problem, you have to instantiate a new meta level. And then you have an infinite regress. And this cannot be solved unless you introduce a cut somewhere. Now, if I put on the engineering hat, then I would say, oh, doesn't matter, just a prior, that's it, full stop, no? But from a conceptual point of view, this is a problem. This is a serious problem because it requires the introduction of a new principle. In this case, there is no such a thing. The model that this is the scenario that this is modeling is an agent that is trying to optimize a utility function, but runs out of resources, and it cannot reason about these resources. Okay, so it's a computer is just running, optimizing, and suddenly, it runs out of resources. That's it. So it better is an anytime algorithm, yeah.
Thank you very much for the interesting talk.
Thank you.